as with all of my tests and quizzes, you don't have to get like an integer number. You could just leave it as in binomial coefficients, factorials, whatever. That might save us all some grief. Looks like some of you are done. Oh, let me get the homework first, and then I'll come get your quizzes. So when we get done after I've got the homework, just feel free to turn your paper over something to go first. If you're not, you can steal over it a little bit more. Close enough? Okay. All right, did I get them all? All right, no one's holding out on me. Okay, let me show you what I've got, and then we'll move on from there. So this is the Uno deck. But as I was writing this down, I realized if you've ever played Uno, there are multiples, aren't there? Like if you like there's 2 or 3 of the same card, like blue draw 2, for example. There's like 2 of them, and so all of a sudden this happened, and I was like, oh, it's too complicated. Yeah, so to actually figure out how many different hands are possible, we'd have to take into account all those multiples, and it's like, well, let's just pretend they're all different, and I just left it like that because I didn't want my head to explode. Okay, so for this one, there's more than one way to do this, so just be forewarned. Here's the first way, or the first way that I came up with. I saw several people did it this way, so let me just explain, and then I'll show you the or. So the first way, what I did was I said, let's ignore the fact that you have these 2 women who don't want to work together, and so you have 7 choose 3 times 8 choose 3. That makes sense because you have the men, the women, done. But then you have to take into account that if you do have a committee where these 2 women are both on the committee, that's not going to work. So we're going to subtract off all the ways that those 2 women could serve together. And the men, no problem with them. But then let's just imagine that the 2 women are on a committee. You need to pick 1 more woman, and there's 6 other women. You're choosing 1 out of 6. And so that ends up being like that. The other way to look at this is we could, wait, did I do it? Oh, I didn't do it right. I'm not done. Well, that's okay. I've got room. I can fix, I think. Can I fix? Yes, I can fix it. Okay, so the other way to look at it is to look at it in a more positive way. And this is more like the adding of the different possibilities. And you should get the exact same number either way. But here you have the men. Once again, men, not a problem. The women, this is if you assume that let's just say that the two women that don't want to work together are person A and person B. So this is person A is on the committee. You need two more women on the committee, but it can't be person B. So there's 6 choose 2 ways of that happening. Then let's move on and say, let's put person B on the committee. And then you need 2 more women, but it can't be person A. But I neglected the last possibility, which is the possibility that we should really focus on if you have 2 women or 2 people who don't want to serve together. In that case, you really should just go with this version or this option, which is we won't have either of them on the committee. And so then, they're disqualified because they can't handle working with each other. So if they're going to be that juvenile. Anyway, either one of those. I love about mathematics is there's often more than one way to go about something, and that you get the exact same number, whatever it is. I saw some 980s. Is that the right number? I didn't compute this, so I don't know. I'm just assuming that since several of you had that, is that right? I don't know. Now I'm not seeing it. Well, oh yeah, let's see. Did this person do it right? This? No, that's not right. I don't know what the right answer. Oh wait, this is the right answer. This person did it right. 1750? Okay, so 1750 must be the right answer. Okay, well anyway, let's move on if need, unless you have questions about this. So this is sort of like, counting is hard. It's not as easy as we might like to think this here. Okay, moving on though. So let me find my next thing. Here we are, we've done that. We're on to multinomial coefficients. So today we're going to finish up this chapter. We're just going to deal with some advanced counting issues, some counting problems, and then we get to move on next time to the axioms and theorems, which is where we get to really deal with how do we know when you're adding or subtracting or multiplying or dividing or whatever. Those questions we're going to be able to categorize things. And one of the things I love about probability is eventually we're not only going to categorize those things, but we're going to categorize the type of problems. Like some problems are like committee problems, but there are other problems that are like dealing, putting people in order. So we'll eventually get there and we'll be able to just make formulas for these things. Okay, so first of all, the binomial coefficients come from, they're called binomial coefficients because they come from the binomials. I think I mentioned this last time, but we didn't have any on the homework, so it'll be on the homework for this time. But just to illustrate really quickly, and then I'll have one for you to do. The binomial coefficients, what you do, let's see, that's too easy, this one. What we'll do is we start with, since this is 4, the 4th power, we do 4 choose 0 times x to the 4th, y to the 0, and then 4 choose 1, x to the 3rd, y to the 1st, and then 4 choose 2, x squared, y squared, and then 4 choose 3, x, y cubed, and then 4 choose 4, x to the 0, but I have no room for it, so it's just y to the 4th. X to the 0 times y to the 4th. And then, so just simplifying that, this is just x to the 4th, 4x cubed y, 6x squared y squared, 4xy cubed, and then y to the 4th. That is the same. That's what this is here. So it's just kind of neat that we can compute these. And since we're dealing with these combinations, then we might as well see how this relates. Now you might wonder, why is it that these are the same as combinations? And the reason is that what you're doing here is you're taking x plus y, multiplying it by itself 4 times, like this. And so let's just take this 6 here. That 6 represents the fact that in order to get x squared, y squared, you need to choose which 2 of those binomials you're going to get your x from. So maybe I'll get my x from this one and this one. And you need to choose which 2 of those binomials you get your y from. So if I multiply those together like that, then I'll get um, x squared y squared. But of course, I could have chosen this one and this one for the y's, or this one and this one for the y's. So you're choosing two of them to get your y, and the other ones you're going to get the x. And so that's why it's the same as the choose. It's the binomial coefficients. So, um, okay, that's just, yeah, that's exactly what that says. So let's try this out with a few practice problems. Let me do this. That one's too easy. Let's do this one. So, oh, wait, before we do that, let me just, I just skipped over this, but I realized I need to at least mention this, that the coefficient of x to the n1, y to the n1 in this expansion is going to be that binomial coefficient only when the n1 plus the n2, whatever those are, equals the n right there. So if n1 plus n2 equals anything else, then the coefficient will be 0. So the only time you have a coefficient is if the sum of these two things is equal to the n, the power. Where is it? There it is. So just to illustrate this, notice that here these two add up to 4, these two add up to 4, they all add up to 4, each of the pairs of exponents, and here that's a 4. So it's always going to add up to whatever the power is. Okay, so let me do this one, and then I've got two for you to do. The first one was too easy, so we'll do this one. Okay, so to do this, if I want to know, oh, yeah, here's the stem of the problem. Find the coefficient of ... There it is. So here we're going to find the coefficient of x cubed y to the fifth in this. So the way I'm going to do this is I recognize, first of all, that 3 plus 5 equals 8. So that means I can use this little formula. Once I know that, I can just write this coefficient like this. It's going to be 8 choose 5, or 8 choose 3. I don't care which way you go with this. 8 choose 5, but we're not done because because of the stuff in the parentheses there isn't just x and y. So now I'm going to multiply by x to the third, and that x there is just this x. I know that's not that big of a deal, but the next one is a big deal. This is going to be negative 2y to the fifth. Now that negative 2y, it's super important that you recognize that that's actually this right there. Oh, I just made it hard to read. I'll make it negative 2y. It's a little bit better. Now that I've got that, I can finish this up. 8 choose 5. Let's see, 8. Just a minute. That's going to be 8, 7, 6, 3, 2, 1. Give me a minute here. 8 times 7 is 56. Okay, so that's 56. X to the third times, I'll put the negative out front because negative 2 to the fifth will be negative 32 in particular. So that's times 32, y to the fifth. And so my final answer, which it's too late in the day for me to do this in my head. So let's clear this. 56 times 32, 1792. Oh, fascinating. 1792 times x to the third, y to the fifth. 1792, the first Congress of the United States. The first congressional elections happened that year, I believe. Presidential election as well that year. Whew. Okay, but anyway, there's that. So see how that kind of shakes out? It's not too bad. Let's do this again. Let's give one for you to do. Once again, stem of the problem is find the coefficient of that in this particular expansion. So see if you can do this. Work with a friend if you need to. So it's especially for really simple. So I class anyway, or this the All right, well, it looks like some of you are done. So let's work through this one step at a time. We're going to start with the fact we want to make sure that when you add the exponents together, you get this exponent over here, the 5 there. So Hannah, did you add those exponents together, the 3 and the 2? Yes. Does it add up to 5? All right, we're good. So we can use this formula. If it had not added up to 5, then the answer would just be 0, because it would mean that this term doesn't exist in that expansion. Okay, so that was step 1. Step 2, we need to figure out what our binomial is. So let's find our next Cooper-Claggett. Wait, there's only one Cooper in this class. Cooper, what's the binomial that I'm going to use for this one?
3x to the third.
No. The choose. 5 choose 3, yeah. So 5 choose 3. Very good. So 5 choose 3 because the big exponent is 5, and either one of these is going to be fine. You can pick either one, you'll get the same answer either way. So very good, 5 choose 3. And then we're going to have to do this, multiply 3x to some power and 2y to some power. So let's get those powers. Next volunteer, Alyssa, what are those 2 powers that we're going to use? Okay, so good. Now, all that's left is just to multiply everything out and get it done here. What is this, 10? 5, 3, 5, 4. Yeah, is that right? 10, and then times 27 times 4, x cubed y squared. Did anyone actually do that on their calculator? Or, I mean, actually, that's not bad. That's going to be, what, 108? 1080, all right? Okay, so 1080. Nice. All right, one more, and then actually one more after that because I'm dissatisfied with the ones that I have here. So let's try this one and see what this one looks like. Okay, so before you start dismissing this as not having an answer, let me just point out something that's a little bit weird about this one. Since there is no y, it's just x minus 7. One way you could do this is you could say that this is x minus 7 times 1 to the 8th power, and I'm looking for the exponent of x to the 7th times 1 to the 1st in this. So instead of a y, I'm just going to use a 1 there. And this is anytime there's not a y, if it's just x plus or x minus something, then really it's okay that I mean, you can make it add up to 8 by doing what I just did there, but yeah, that's what you've got there. So this one you can use the formula, even though at first glance you might say, wait, this violates your little rule that you have to add up to 8. Well, I can make it add up to 8 by just throwing a 1 in there. All right, Nolan, what do you think? What's the binomial coefficient going to be? The choose 8 choose 7. Very good. So 8 choose 7, and then we need to stick something in here in the parentheses. Evan, what am I going to put in this parentheses here? The first one, just x, and what's the power for the x? All right, very nice. And then one more parenthesis here, and whoops, I've already bugged you, Chelsea. Wait, didn't I bug you already? That's all right. You can do it, I'm sure. What goes in that second parenthesis? 7. Very good. And specifically, it's -7. So we've got to pay attention to the negatives there. And then what power, by the way, Chelsea, would that be? To the first power. Very good. Yeah, so that helps you figure out. So now we do have 7 plus 1 is equal to 8. So everything's good. So this is going to be 8 times x to the 7th times -7. And so what's that? -56 times x to the 7th. Does that sound right? That's a 5, by the way. 5, 5, 5. All right, so one more, just because these are kind of all the same, similar. I guess that last one was a little bit different. Let me just change this around just a bit. Change this to 2. So what's the coefficient of x squared y to the 5th in the expansion of x plus y to the 6th? Take a minute, see if you can work that one out. And if you've done it, it shouldn't take you much time at all, probably. But Sarah, did you figure out what that is? It is just 0. Why is it 0?
Because 2 plus 5 does not
equal 6. That's right. Well, yeah, I picked it that way. So yes. So that's 0. Done. Very nice. Okay, so that wasn't too bad. So let's do some multinomial coefficients. Oh, it looks so gross. Okay, well, let me just explain briefly. I know that looks terrible, but it's the same exact formula. So the same exact, except for the fact that we're going to use this notation for a multinomial coefficient. Specifically, if you have, so think of it, multinomial coefficients, one way to think of it is if you have, say, a group of things that you're going to put into different piles. So a binomial coefficient, you have some stuff, and you're going to separate it into 2 piles. Here, we're going to separate it into more than 2 piles. And so you have the n is the number of things that you have, and then these are the sizes of the piles. And you can kind of see here that this kind of follows the same pattern as the number of permutations of the letters of your name. You start off with n factorial, that's all of the letters, but then you divide by the duplicates. The duplicates are kind of like the groupings that you have of the different things that you're dividing these into. So we'll see an example of this in just a bit, but for now, let's see how this works in terms of the multinomial coefficients. So let me do this first one. I know it looks really, really crazy, but the same rule applies, by the way. So for example, down here, the only way to have this be non-zero is if the numbers, the exponents, add up to that exponent there. And if there's like a constant in here, then it's kind of like you get a freebie, if you will, and it can be, yeah, the constant kind of allows you to not add up perfectly until you put like a constant in there. But yeah, let's go down here. Let's go to the top one. Do this one first. So the first thing to note is that I'm going to have 7, and I'm going to choose, wait, how does this, what's the notation? Sorry. Yeah, okay. Yeah, okay, we'll do that. 7, and then we've got 1, 5, 1, which is confusing. So there's that multinomial coefficient, x to the first, y to the fifth negative z. Notice that the negative is associated with the z to the first. So there's the first step, but then I'm going to actually compute I'm going to compute the value of 7, choose 1, 5, 1. So that's going to be 7 factorial over 1 factorial times 5 factorial times 1 factorial. This is going to be x, y to the fifth z, and I guess there's a negative there. I'm almost done. So you could do this yourself. 7 factorial is 5,040. 5 factorial is 120. And when you divide those things, I think you get 42. Guess we'll find out. If anyone finds a mistake, you can yell at me. Negative 42 xy to the fifth z is my final answer for that coefficient. Now, of course, this expansion is going to have way, way more terms in it, but that's just one of those many terms. Let's see. Is this really that important? Let's do these two. Let's not do them all. This will be fun. Oh, interesting. Oh yeah, I like that. Yeah, let's do the top one is kind of interesting. Both of these are interesting. But top one, they're both interesting. So take a minute. You can do them both, or whichever ones you can give up if you want. But here. Okay, I'm going to set this up because this is a little bit more complicated. I think that unlike sorry about that, zoom back in. Unlike the binomial coefficients, that this one might be best done sort of backwards in a sense. And what I mean by that is I've got here the three things within these parentheses. So I have 3x, I have 2y squared, and I have 1. So I've got those three things, and I'm going to be multiplying them together. And then after I figure out the exponents, I will deal with the multinomial coefficient, which is going to have a 4 because of that 4 there. So let me find someone to help me. How about Zane? Zane, when I do this, how many x's do I need in my final answer? Because I want this coefficient, the coefficient of this. So what's that? Yeah, I need 3 of them. Very good. So I need 3 x's. So whatever I do, I'm going to need to raise this to the third power. We'll come back to exactly what that means in just a minute. And then I need to know how many y squareds do I need. So that's next. So Alyssa, how many y squareds do I need in my answer? Well, they come in pairs. So what? Yeah, just the 2y squared. Okay, yeah, sorry, maybe I'm communicating poorly. So yeah, to generate this x cubed y squared, I need 3 of these, 3 x's. But since the y squareds already come packaged together in a pair, just y squared, I just need to have that. Ignore this coefficient, that 3 and this 2, they're irrelevant at this point. All I care about is I've got x cubed from here, and I've got y squared from here. Now, the last thing is I need to figure out what the exponent of 1 is. Technically, it doesn't matter, but I want to make sure that it's going to all add up. And so what exponent do I need to have for this 1 here? That's the thing that we need to figure out. And I'll bet you Rachel can tell me. Rachel, do you know what the exponent is for this? It is 0. Why is it 0? Yeah, they all have to add up to 4. And so that's going to be 0. That really doesn't matter with the 1 here, but if that was like a 2 or a 3, it would make a big difference. as to what that was. But here, it doesn't matter as much. Oh, come on. There we go. So this is 0. There. Now I'm going to set up my multinomial coefficient. So I have 4 on top. And then inside, underneath that 4, I'm just going to put these 3 exponents. And that's going to tell me what I have here, 3, 1, 0. So that's going to be 4 factorial over 3 factorial times 1 factorial times 0 factorial times 27x cubed times 2y squared. 1 to the 0 is 1. So we're all set there. So then you just have to do this calculation. The only thing that's a little bit weird is 0 factorial. You can do it on your calculator, and you find that 0 factorial is 1. It's a couple of different ways of figuring out that that's the case. Let's see, what's the easiest way? Maybe just if you're not, this may not be that convincing, but let's do this. 4 factorial is 24. 3 factorial is 6. 2 factorial is 2. 1 factorial is 1. And so I ask, what is 0 factorial? Well, check it out. Divide by 4 to get this one, right? And then divide by 3 to get this. Divide by 2, and then you're going to divide by 1. 1 divided by 1 is 1. Here. So we're all set. Another way to think of it is it's the number of ways to rearrange all the people standing over there. There's no one over there, but in a sense, there's one way to arrange them, and that's what you're looking at right now. So I know that's a little bit worse. I don't like that explanation as much as seeing the progression. But either way, I guess we're going to have 4 factorial, which is 24, divided by 3 factorial, which is 6, times 1 times 1. So that's 4. 4 times 27 times 2, 4 times 54 is 216. X cubed y squared, I think. So there we go. All right, so see if you can do this last one. This last one is a little bit more interesting than this one. Maybe I'll leave that up there. Give you another minute or two, but we do need to move on to some, in the last 8 minutes, some examples of other applications of this other than these things. All right, well, in the interest of time, let's walk through this. I bet we can do it together. I need to get my phone going. It's really annoying to me that it keeps repeating the same people. Sydney, what do you think is going to be the exponent of W for this expression down here? And it should match this right here. Yeah, it's going to be 1. What about the exponent of 3x? So yeah, that's the pattern. And then, of course, a 1 and a 1. But now the hard one, we have to figure out what the exponent for 4 is. So let's see. Take a minute. See if you can take a guess. And then, yeah, I'm sick of this thing doing it. I don't know who I haven't asked yet. I haven't asked you, Reagan. What do you say? Do you know the exponent of 4? 7? Where'd that come from? So 1, 2, 1, 1. Those add up to 5, and we need another 7 to make it add up to 12. That's beautiful. And so the final answer here is whatever this is, 12 factorial over 2 factorial. I'm going to leave off the 1 factorials. 7 factorial times 4 to the 7th times 3 to the 2nd times 2. Wx squared yc. There. So this is the answer to this one. Whatever that number is, and I don't even want to know. It's 4 to the 7th. That's huge. It's 2 to the 14th. I'm not going to do it. I refuse. Okay, so there's that. Let's see what other, let me see. We have time for a couple of applications. Multinomial mat ball. Oh yeah, why not? Let's do this. So a gym teacher must divide a class of 48 students into 8 teams for of 6 for a mat ball tournament. How many ways can the students be divided? Well, here, once again, as I mentioned, this is very similar to the multinomial coefficients. You're trying to decide where everyone goes. So you start off, by the way, there's a way you can do this that doesn't use multinomial coefficients. So if you prefer, if you've got another way of doing this, it's fine with me. But I'll show you the multinomial way. Start with 48 students, and you have 8 teams of 6. Oof. So I've got 6 students, and then 6, and then 6, and then 6, 6, 6. Wow, there's 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Whew. There's the number that we're looking for. It's a lot nicer if we just write it like this. 48 factorial over 6 factorial to the 8th power is what this is going to look like. Wow. All right, that's not too bad. I mean, it kind of makes sense. As long as we're talking about mat ball, what if we set up a single elimination tournament? How many ways could we do that once we have the teams set up? So that's another question that you might have. And this one, yeah, I guess you have to know what a single elimination tournament is. This is like setting up a bracket. Oh, wait a minute. 48, 8 teams. Oh, there's 8 teams. Good. So those 8 teams, you're going to start off with four matches. 1, 2, 3, 4. And then, wait, how does this work? Is this the way a bracket looks? Okay, yeah, you can see how sporty I am. And then this is the last thing. Okay, so the choices you have to pick 2 of the teams to go here. So that's going to be 8, choose 2. Oh, let's just pick all 4. All 4 of the bracket, the first level. So 8, choose 2, 2, 2, and 2. But then, once you've done that, you have to decide how to pair it, because the winner of this could be paired against the winner from this, or the winner from this could be paired, and so on. So to do that, you have to say, okay, there's 4 winners of those 4 matches, and they can be paired up in 2 and 2, and then the last match, whoever wins the previous one, there's no options of the way you're going to set up that bracket. So that's going to be the total number of ways. I don't know how many that is. Let's see. Yeah, I don't want to do it in my head. But there's quite a few ways to set up a single elimination tournament. One more, and then, wait, is it too late? It is not. We have 2 minutes, so there's enough time for one more if this thing cooperates. How about MVNU multinomial multimedia? No. Let's do allocation of resources. No, that's going to be too complicated right now. I guess we'll deal with it on Wednesday. But yeah, this one. We have 20 classrooms. I have 10 regular teaching stations, 5 smart boards, 3 immersive IMAX screens. Yeah. And then 2 computers with holographic 3D displays, if you can imagine, I don't know. And I want to know how many ways can I allocate those classrooms. And so you're going to choose, so basically it's just you've got 20 things that you have to allocate to 20 classrooms. And 10 of those are going to get the teaching stations. 5 of them will get the smart boards. 3 will get the IMAX screens, and then 2 will have these holographic displays. So whatever that is, that's the way that's going to look. There will be other questions. I forget what I put on the list here, but if there's anything that doesn't quite fit this pattern, be sure to look in the book. There are some examples that are similar to the problems that I assigned. Do your best. We'll pick up the pieces. We always do, don't we? I don't let you dangle. So do your best, and then we'll pick up the pieces on Wednesday. And so let me stop the recording in case you want to come talk.